What are you thinking about?
So now we have to generalize to additional interactions. We're done with a single spin, except for relaxing. And for more than one spin, for most of what we'll need to do, we can work in what's called the product basis, in which we build up the wave functions and the operators for more than one spin by using what's called mathematically the direct product, which is indicated by the circle with the little x inside. And we can build up direct products of the cats or the bras, and we can build up direct products of the operators. And the operator here, well, first you can see here, the direct product for the vector is just a stat of all the individual vectors. And the direct product for an operator is each element of the first operator is expanded up to a matrix by multiplying it by the second operator matrix. It's easier perhaps to see over here. So if we want the wave function for two spins, each of which are in the alpha state, we have alpha state, direct product alpha state. We take the first one and stack it on top. Or take the first one and this element, it's multiplied by this vector. And then this element, it's multiplied by that vector. So we end up with, we take this one, multiply it by 1, 0, we get 1, 0. And then we take a 0, multiply it by 1, 0, we get 0, 0. Whereas here, for example, alpha beta, alpha is 1, 0, beta is 0, 1. We take the 1, multiply it by the 1, 0, we get 0, 1. We take the 0, multiply it by a 1, by 0, 1, we get 0, 0. Similarly here, beta alpha 0, 1, 1, 0. 0 times 1, 0 is 0, 0. 1 times 1, 0, 1, 0. And then beta beta, 0 times 0, 1 is 0, 0. 1 times 0, 1 is 0, 1. In the ordering, then we have alpha, the one position here is alpha alpha, one position here is alpha beta, one position here is beta alpha, one position here is beta beta. So it means that as I move down the column, the rightmost spin state changes first. And that'll always be the rule for how I decide to order things. So the rightmost element changes first. And so first I change this alpha to beta, and I get a 1 here. And I change this one to beta, and I get a 1 here. And finally, both are betas, I get a 1 on position. So this then, for two spins, are my 4 F's, or 4 wave functions. And if I turn these into the row vector, those are the bras or the complex conjugate. Now, if I want to know, for example, what one of the operators is for a single spin when I have more than one spin, then I have to do the direct product with a bunch of the identity operators, in which my operator comes in the correct position in the chain. And again, for 2, it's pretty easy to see. If I want, suppose I have 2 spins and I call the first one I and the second one S. If I want to know for 2 spins, the matrix representation of IZ, I have IZ direct product with the identity operator essentially for the S spin. And if I wanted SZ, I have the identity operator for the I spin, direct product with the 1 spin operator for the S spin. So the order matters here a lot. And if I decide that I'm going to write I then S, then I have to keep that ordering always. So we'll use mostly I and S. Sometimes we might use I sub 1 and I sub 2. And if I decide I sub 1 comes before I sub 2 in my symbols, then I have to keep that ordering always, because these direct products don't commute with each other. It means then if I write down an operator IZ, the matrices are different if I'm talking about 1 spin or 2 spins or 3 spins. When I was just talking about 1 spin, the matrices were 2 by 2. Now when I'm talking about 2 spins, you can see that they're 4 by 4. And when I talk about 3 spins, they're going to be I guess 8 by 8. Yes, 8 by 8. So the dimensions of the matrices get larger. In our conventional language, we would always just write IZ regardless. It would be clearer if I wrote IZE to remind me that I really have the direct product with the identity operator for the other spin. Or if I had 3 spins, I, RS, and I wrote IZ, I really meant IZEE. Or if I wrote RZ, I really meant ERZE. And if I meant SZ, I meant EESZ. That would tell me, that I really have this expansion. But we don't do that. You have to remember that the E's are there, even though we don't tend to write them, because sometimes it becomes important. But here then, the rule for direct product says, I take the first element of this matrix, which happens to be a 1, and I expand it up by multiplying this element by the second matrix, which happens to be the identity. So here I get a little 2 by 2 block that's 1 times the identity matrix. And then I take the second element and I also multiply it by the identity. And I get another 2 by 2 block that's all zeros in this case. And then another 0 times this gives me another 2 by 2 block of zeros. And then a -1 times the identity gives me this block that is all minuses. When I have just 1 spin, and the IZ operator was 1 and on the diagonal, and then a -1 on the diagonal. And in the column vector, I would associate those, the first position as representing the population of the alpha state. The second diagonal position, the population of the beta state. And the minus sign tells me that IZ magnetization is represented by the difference between the population of the alpha state and the population of the beta state. Well, remember at Boltzmann equilibrium, when everything was proportional to IZ, the diagonal elements were the populations of the Boltzmann populations. And then IZ magnetization is proportional to the difference in those populations. So when I just had the one spin, this is representing population of alpha, this is representing population of beta, and that difference is then IZ magnetization. What does this mean? Well, this, remember my indices change from right to left. Well, this is the alpha alpha state. Here's the alpha beta state. Here's the beta alpha state. Here's the beta beta state. So both of these states, the I spin, the leftmost designation is the alpha. And here the leftmost designation is beta. So this says I take all the alpha populations of the I spin, subtract off all the beta populations of the I spin, and that gives me the magnetization of the I spin in the two spin state. So here I've done the two spin SZ, do the same thing. I get this matrix. This is alpha alpha. This is beta alpha. This is alpha beta, and this is beta beta. So this says that to get Z magnetization, I take the populations of all the states where the S spin is in the alpha state and subtract off all of the states where the S spin is in the beta state. Yep.
So I wanted a clarification, maybe it relates to back to the previous lecture. By population, we specifically mean number of spins on a particular state.
Right, and since we've subtracted out, for our purposes right now, we've subtracted out the diagonal term. We just have, what we mean here are the deviations from equally populated states. So the amount of excess in the alpha state or amount of excess in the beta state. And normalized so that the here we normalize to some trace. So we take the product of IZ and SZ, we take the product here and take the trace. We take here IZ times IZ and take the trace. We're going to get 1 because the diagonals will all become unity when we take the square. The sum is 4. The square of a half is a quarter. So these happen to be normalized to be trace of 1. Their squared magnitude traces 1. That won't always be the case. You can always make it the case, but sometimes when we do that, you get a bunch of square roots. So we don't necessarily normalize properly. It's important that all our operators be normalized the same, but not that they necessarily be normalized to 1. In this case, they've been normalized properly. So if I wanted to know the actual populations, then I have to put back in all these factors to get the real numbers. So these are just measuring, telling me kind of a relative measure.
So if we say the populations in alpha beta, that means we have certain number of spins in the alpha state and certain number of spins in the beta state with respect to some sort of normalization.
And of course, the sum has to be a constant because we can't make spins go away. So we could also here have an operator E direct product with E. and that would just be 4 ones on the diagonal. And that would just reflect that we have a constant number of spins. E, direct product with E doesn't change in our NMR experiments. We're generally not interested in it. But if we have or here we have this diagonal element, these diagonal elements. Here we have SZ. If we multiply these and take the trace, we're going to get 0. Because here we're going to get the product plus 1. 1 times minus 1 is minus 1. Minus 1 times 1 is minus 1. Minus 1 times minus 1 is plus 1. So these are orthogonal to each other. I mean, we set the operators up to have this property. And then obviously, if we did E times Z, where we have 4 ones, that's going to be orthogonal to each of these. But if we have 4 numbers, 4 sets of 1 on the diagonal, there must be a 4th set. There must be another set that's orthogonal to all 3. And that turns out to be this, IZ to IZSZ, 2, which is just a number, IZ direct product with IZ. So here I take a 1, and I multiply it by this matrix, which would be the operator for SZ. And I get this, and then I take this, multiply it, I get a block of zeros, another block of zeros. And here I have minus 1 times this. So I get this. So this is a different pattern of 1s and minus 1s. And you can convince yourself that this is orthogonal to either SZ, IZ, or the identity operator. So this is something else. This says we take the population of the alpha-alpha state plus the population of the beta-beta state and subtract the population of the alpha-beta state and the population of the beta-alpha state. So this is something new. We haven't seen it before. Obviously, it didn't exist when we just had 1 spin. If you went back to the populations, the equilibrium populations, we derive the Boltzmann equilibrium population, you would discover that this has at Boltzmann equilibrium 0 amplitude. Everything cancels. Or at Boltzmann equilibrium, we don't, whatever this thing is, we don't have any of it at Boltzmann equilibrium, at least at high temperature, where we can expand the Boltzmann factors, first order. So this is something new, but it doesn't exist. It'll turn out to be incredibly interesting to us because it's symmetric if we swap the alpha and beta states. Here, alpha, alpha, if we swap, that's alpha and beta, it just becomes beta, beta. I mean, if we swap alpha with alpha, I and S, we still are alphas. Here, if we swap alpha and beta, we just get this one. And if we swap alpha and beta, this one becomes this one. And if we swap beta and beta, we get beta. So this operator is symmetric to swapping the alpha and beta states. And that'll turn out to be really important. At one level, we've been driven to think, even though it's not present at Boltzmann equilibrium, we're driven to think it might exist.
Hello.
As it's going to exist.
Hello. Hello.
Yes.
Yeah. Can you hear me?
Our question?
Yeah. This may not be a good question, but I was also wondering if this beta state and alpha state has something to do with the gamma of the particular nuclei that one is interested in.
So if we're talking about spin 1/2 particles, then alpha is always just the state with the spin magnetic quantum number plus 1/2, and beta is the state with the magnetic quantum number minus 1/2. Where the gammas come in is, for example, here. If we want to know for a given nucleus how much population there is, or not here, so here, for a given nucleus, if we want to know how much population is in the alpha state, that'll depend on gamma, because gamma times B naught or minus gamma times B naught is omega naught. So whether we have low population of the alpha and beta state at Boltzmann equilibrium or high population depends on gamma. But our labeling of the states, beta and alpha, they're just always plus 1/2 or minus 1/2. Does that help?
Yes, but does it have anything to do with, let's say, whether the gamma is positive or negative, like in the case of nitrogen? Does it change, or does it mean that it has this swap that you talked about? Does it have anything to do with it?
So if we have, when I draw the energy levels, where do I have the energy level? Picture. So when I've been drawing the energy levels, you have to look back in lecture number 1, I've been drawing alpha to be the lower energy state and beta to be the higher energy state. But that's for a positive gamma. So if gamma was negative, beta would become the lower energy state and alpha would become the higher energy state. In most NMR experiments, we don't really care about that. But that is important in TROSY experiments. So in the TROSY experiment, which line you think is the so-called TROSY line, and which line you think is the anti-TROSY line, the narrow line and the broad line. The mapping of the resonance back to the particular spin states requires you to pay a lot of attention to the sign of gamma. So in the beginning, when TROSY was first invented, papers, including some of my own, kind of randomly assigned which peak was which. And then eventually it got carefully worked out. So now we know which is which. That's, you know, one of the few cases where you actually care. It's also important when we get to relaxation theory. There it makes a big difference whether we're talking about positive or negative gammas, because that'll make the Larmor frequencies positive or negative, and that'll change what we think are double quantum versus single quantum contributions in relaxation theory.
Yeah, thank you so much.
Mm-hmm. Did this, did that. So we can build up all these tables, and then we have a rule for how we do the calculations. And the rule is really simple. The operators, say, that have a symbol I, act on the part of the wave function that belongs to the I spin, and the part of the operator that acts on that has the S part acts on the part of the wave function that came from the S part. So that means, for example, if I have two operators A, B here, I always write that A goes with the first spin, which I'll call I, and the B then is associated with the S spin. And here in the wave function, the first index goes with the I spin and the second index goes with the S spin. So then I just have to operate with the A operator on the I spin wave function and with B on the S spin wave function. So I can kind of take apart. So this says AB, I really mean the direct product of A with B, which will be a big matrix. But then I can take them apart to their individual bits in doing the calculation, and then take the answer and blow it back up to the bigger matrix. So that makes life really easy. It will basically be doing the operator calculations piece by piece. I spin acts on I spin, S spin acts on S spin. So here's an example. So if I want to know what happens to the alpha beta state when I operate with IZ, of course, I could take my big matrix, the matrix for IZ for the 2-spin case. I can take the wave function for alpha beta for the 2-spin case, multiply them together, and I recognize I get back 1/2 times what I started with. Or I could say, well, this really says I have IZE, because the E is always there if I don't have an S representation. So the IZ acts on alpha, and I know IZ acting on alpha gives back 1/2 alpha, and E acting on beta gives back beta, and that's shown here. So IZ acts on alpha, I get back alpha. E acts on beta, I get back beta. So I then have the direct product of 1/2 alpha with beta, and that's the state that I write like that. Yep.
So when we only have one spin operator, like in this example IZ, are we always multiplying that with E on the right side, or like?
So it depends on my ordering. So if I have 2 spins and I say my first operator is I and my second operator is S, if there's no S in my operator symbol, I have to know that there's really an E there on the S side. Similar, if I wrote SZ here, I have to imagine that there's an E on the other side. And if I have 3 spins, then there could be 2 E's running around. I have to keep the ordering always the same. And that's really the only tricky bit in NMR. So here's another example. Here's this operator that we said must be there, even though we've never seen it before. And again, if I want to know how it acts on the alpha beta state, I can take the full matrix, multiply it by the alpha beta state, and find out that I get back -1/2 of the alpha beta state. Or I could say what I really mean is that I'm going to take IZ operating on the alpha state, SZ operating on the beta state. I have this normalization factor of a 2 that went in there just to make everything have the same norm. So I have 2/2 alpha, direct product with -1/2 beta. We should have a parenthesis here. So I get -1/2 of the alpha beta state. So on a computer, this is easy. The computer doesn't care how big the matrices are. But when I'm doing it by hand, this is obviously easier. I do it piecemeal. I operates on I, S operates on S, and then I put the results together. And I just have to remember that there could be this E running around. So then here's the scalar coupling Hamiltonian. The scalar coupling Hamiltonian is 2 pi, the sum over all the spins we have of the scalar coupling constant, Jij, and then 2 spin operators, I sub I dotted with I sub j, where dot is the dot product. The 2 pi comes because for historical reasons, people measure J in hertz, and we have to convert to angular units. If we work on a big enough magnet, then this simplifies because we only need the part that commutes with the static magnetic field, which means only parts that are Z operators can survive what's called truncation. And Ann will probably talk more about truncation at some point, because it's very important in solid state NMR. So in what's called the weak coupling limit, if the coupling constants are much smaller than the difference in frequencies of the 2 spins that share the coupling, then we're in the so-called weak coupling limit, and we can throw away the X and Y parts of this dot product and just keep the 2 ZZ parts. So for example, if we have a proton-proton coupling, say it's 3-bond proton-proton coupling between the amide hydrogen and the alpha hydrogen. Those maximally get to be about, let's say, 12 hertz. And then we have, what's the frequency difference between an alpha hydrogen and an amide hydrogen? Well, the amide hydrogens are somewhere around 8 parts per million. Let's say the hydrogens are perhaps as large as 5, so maybe 3 parts per million difference. On a 500 NMR spectrometer, 1 part per million is 500 hertz, 3 parts per million is 1,500 hertz. Clearly, that's much, much larger than the coupling constant at 12 hertz. As we go to bigger and bigger magnets, the scalar couplings are the same, but the frequency difference gets larger and larger, scaling linearly with the size field. So the bigger the magnet, the more likely you are to be in the weak coupling limit, which is a nice simplification. At 900 megahertz, there's only a few couplings in the aromatic rings, like in the phenyl ring, that are still in kind of strong coupling limit. Everything else is weak coupling. So we'll only worry about the weak coupling Hamiltonian for a while. And that means for solution NMR, in the weak coupling limit, this is the Hamiltonian. We have the frequencies, and I could put the chemical shift in here. And we have the J coupling. And then we'll switch to the rotating frame. So in the rotating frame, we'll just have the offset here, capital omega, and nothing happens to the J coupling. So then, in the rotating frame, we're in business. So here, the J couplings are independent of time. So evolution of the J couplings is given right away by our simple formula, where we plug in the expression for the Hamiltonian, and we have our starting density operator and our final density operator. We can figure out what this exponential means by expanding the exponentials in Taylor series and working out term by term what's happening. I've done this for you. For 2 spins, this exponential operator turned out to be something that depends on the sines and cosines of the scalar coupling evolving in some time. And then we can ask, what does this mean for evolution of our operators? And then I can draw a picture. The picture I can end up drawing is the operator associated with the scalar coupling has the form 2IZSC. When I look back here at the Hamiltonian, I have this 2 that came from the fact I needed to convert hertz into angular units. But it's convenient for me to put the 2 over here with the operators. And that gives me the right normalization so that these 2 products of an IZSZ has the same normalization as IZ and as SZ. And I need to maintain that. It's just luck for me that I had this 2 there already that I could incorporate. And that's why when you see the evolution here of the cosines and sines, you might think there should have been a factor of 2 here that would cancel this 2, but there isn't, because I took that 2 and put it somewhere else. So I end up with a picture that looks like this, that says, if I let the scalar coupling evolve, some operator that looks like IX is going to end up evolving to an operator that looks like 2IYSZ. And if I have an operator that started as IY, it's going to evolve to where it looks like minus 2IXSZ. And an operator that started as 2IXSZ, whatever that is, would then evolve to be plus IY under the scalar coupling. And let's switch to the board for a moment to try to indicate really what's going on here. Share. Well, I say that I start out with SZ magnetization. Now, my energy level diagrams, they look like this: alpha, 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 beta, beta, alpha, beta, beta. Now, let's make it IZ. Now, IZ, we said, was associated with the population difference between the I spin in the alpha state and the I spin in the beta state. So here's one transition where the I spin, you have to stand and see what it's going to be. The I spin goes from alpha to beta, while the S spin stays alpha. And then here's a transition where the I spin goes alpha to beta, but the S spin is in the beta spin. And then the coupling means, the scalar coupling means that these two transitions have different energy. In the absence of the coupling, they would have the same energies. But in the presence of the coupling, they have different energies. And doesn't matter so much, but depending on the sign of the coupling, these both move up and these both move down. And I've done it backwards. These both move up. And these both move down for a positive J coupling. Yeah, the picture of the notes is better. So we actually have two different energies. And that means if we apply a 90-degree pulse and say along Y and generate IX magnetization, there's really two kinds of magnetizations here because they're going to process at two different frequencies. The part of the magnetization here is going to have a slightly smaller frequency than the part of the magnetization here, which is going to have a slightly larger frequency because this energy went down, this energy went up.
We need a higher contrast pen
Yeah.
and a magic angle. I mean, it's kind of visible. You can read it, right, Krishna?
Yes, I can read.
You're in the right seat. Is this any better? You're doing okay.
Well, I'm worried more about the people online.
Exactly. Oh, this is so much better. Thanks, Ern.
So I would like my notation to somehow take into account that I'm going to have two different frequencies. And in fact, my notation magically takes care of that. Because if I think that IZ is really IZ operator direct product with the identity operator for the S spin, one way of writing the identity operator for the S spin would be that it's the sum of S alpha, S beta. That I have an operator that represents the alpha state of the S spin and an operator that represents the beta state of the S spin. And the sum has to be equal to unity. It has to be the identity because the spins are either in the alpha state or the beta state. And now I say, looking at my energy diagram, that this one has a frequency, whatever the I spin frequency was going to be, minus pi j, because that's the change in energy here. And this one is going to have a frequency omega I plus pi j. When I look at the spectrum, I'm going to see two peaks. And their splitting is going to be 2 pi j, or in hertz, the splitting is going to be j, back what I expect it to be. Now, to a very good approximation, S alpha has a population of a half, minus a tiny bit, or plus a tiny bit. S beta has a population of a half, minus a tiny little bit. We don't really see that tiny little bit here. So these look to us to be exactly the same height, and that matches what you expected from organic chemistry. And if there's a coupling, you see a doublet, then they look like they have the same intensities. So our symbols have somehow magically matched what we know we see on the NMR machine. We know we're going to see two different frequencies separated by pi j. I just invented this direct product and put these together and say that the identity had to be S alpha plus S beta. But at the end of the day, it tells me what I see on the NMR machine. So at least within the world of NMR, this was the right thing to do. So now, what's going to happen? Now I let this evolve for a while. Let me pretend that I'm on resonance with the I spin, so omega is 0. I'm just going to see the coupling. So here, if I look down from the top, here's X, here's Y. I started with magnetization on the X-axis, but now I know there's two pieces of it. And one of those pieces rotates with the frequency minus pi j, and the other one rotates with the frequency plus pi j, if I'm sitting right in the middle on resonance with the I spin. So if I wait a little while, this one rotates this way, and this one rotates this way. And I'm going to wait the magic amount. I'm going to wait a time I over 2j. So an angle is always a frequency times a time. So here's my frequency, ij, times the time, 1 over 2j, equals pi over 2. So this one will rotate by 90 degrees. This one will rotate by minus 90 degrees. And my picture at that point is, my drawing, this was the positive one. So here I then end up with Iy S beta. And over here, I have minus Iy S alpha. Everybody happy with that? One rotated by plus 90, the other one rotated by minus 90. But this says that my new state is Iy minus S alpha plus S beta. And I'm going to factor out a minus 2 and have minus 2 Iy 1/2 S alpha minus S beta. And I'm going to call this SZ. So I've created a new state, minus Iy SZ. And somewhere along here, I got the signs wrong, but it doesn't matter. This says, now suppose I now measured, turned on the receiver. What was I going to see? This says, I'm still going to have a doublet, but now one peak is positive and one peak is negative because of this minus sign. And again, I can go to the spectrometer and easily do this and show that if I do a 90-degree pulse on resonance, wait 1 over 2j, and then start acquisition, I'm going to see the doublet where one peak is up and the other one is down. So again, all I've done here is manipulate these symbols as if they made sense algebraically. But the end result I can confirm just by going to the spectrometer. So again, at least within the confines of NMR, this was the right thing to do. And now if we go back to the picture or to the notes. We then say, for our two-spin system, we recognize that IX represents, in some way, a doublet where the two members of the doublet are both positive, or both have the same phase. And this guy over here, then 2IYSZ, represents magnetization on the y-axis, but the two doublet components point in opposite directions along the y-axis. And if we took their spectrum, took the NMR spectrum at that point, we would see that one component was up and one component was down. So in our language, one component up, one component down is called antiphase. Both components up is called in phase. And this picture says that if we start with IX, in here we'll have pure anaphase, but somewhere in the middle we're going to get a mixture of the two. And the mixture is going to be cosine IX cosine IJT plus 2 IYSZ sine pi JT. And I just got the sign wrong over there. In the picture. Fixing minus signs is a job for students. And similarly, if I started with IY, after a time period 1/2J, one component is going to be pointing along minus X, and the other component is going to be pointing along plus X. And if I take the spectrum, I'm going to see again an antiphase doublet. It'll be 90-degree phase shifted relative to my first spectrum, and then I would apply a 90-degree phase shift. So the symbols, the important thing is the symbols have a very direct connection to the NMR spectrum. It's not as abstract as it seems. We start with quantum mechanics and do all this algebra to get to the Liouville von Neumann equation, and we solve that equation. And everything can seem abstract, when in fact, these operators are directly connected to what you can see on the NMR machine. Questions online? This is probably the most important 10 minutes of the semester.
I'm a little confused. Like, so if you don't have the delay and you just start with IX and let it evolve, you're seeing two peaks that are in the positive. But if you wait a certain amount of time, you start to see one in the neck. Like, that doesn't, it's a little hard to conceptualize.
So the question is, if I apply a pulse and immediately turn on the receiver, I'm going to see the doublet, both peaks positive. Now I apply the pulse, I don't turn on the receiver. I wait a time period 1/2J. And now I turn on the receiver. I'm going to see one peak up and one peak down. And the picture is because one peak is rotating at plus pi j and the other one's rotating at minus pi j. So after 1/2J, they've rotated to where they're 180 degrees out of phase with respect to each other. And that'll mean one will look positive to me and one will look negative to me.
It's because they're 100 degrees out of phase. I see.
When I turn the receiver on, it's going to look like one is generating a positive signal, the other is generating a negative signal. So all of our kind of mathematical manipulations with these symbols are really just a way of keeping track of what these individual magnetization vectors are doing. The magnetization vector whose partner is in the alpha state and the magnetization vector whose partner is in the beta state. We just have just have to remember that S alpha plus S beta is the identity, and we usually don't write the identity. And 1/2 S alpha minus S beta is Z magnetization. We can interchange as we need to. Everybody happy online?
Yeah, I'm good.
Oh, okay. I have a separate lecture that kind of expands what I did on the board with what these magnetization components are doing. So I'll upload that to the Dropbox so you can see it. Yeah, it basically does what we did on the board. So then we can go on and do just the one pulse experiment with 2 spins. So now our equilibrium density operator has to be 4x4. And again, these are just populations of the alpha alpha state, alpha beta, beta alpha, beta beta states, where I've kept the omegas just to keep the 2 spins separate from each other. But if I wanted the real populations, remember I have to put back in. Yep.
Sorry, it's not full screen.
Oh, something's happened to you. I see. You see my notes. How did this get switched?
You do swap displays.
Pardon?
Is that button on your computer? Swap displays.
No, that is not on my. Okay. Oh, wait, now I can see. Okay. Is that better?
Yes, thank you.
Oh, no, now you guys are lost. Here. Well, now my computer's right and both of those are wrong. Now let me try swapping displays again. Where did that go? We just try. Let's swap this button behind it. You see if directions are provided.
This one.
Well, somehow, when I came back from when I switch here, I get this and they get this. We're swapped.
Yeah, we might need to do the sharing and get that again. Up to sharing and then enable it again.
I think he said,
It was right before, but then when I came back from the border, it's crazy.
Okay, post pressing.
Right, it's still,
Yeah, it's a picture that is what he's made, because it's showing the next line. And there's some. There's something that we should. Something gotta be something with that power plant.
Well, first, let's. Wait a second.
This one. Not this one.
Well, it's pretty big for these people. I think they're okay.
Okay,
Don't worry about this
okay.
next time.
Well,
The only thing is you probably can't see what the next slide.
Well, that's okay. I know what they are. That's the least of my problem. Where we went. Sorry about that, but none of us know what happened. So as I was saying, these diagonal elements are just the Boltzmann populations. But of course, I've left out the KT and the H bar. If I wanted to know the real populations, if we come back where we found the equilibrium density operator, I would need to add in H bar, the number of spins, and KT to get real numbers. So here, I just have the relative numbers. And many times, you know, if it was a homonuclear system, I wouldn't even show the W's because the W's would be the same for two hydrogens, for the omegas. And then if we want to do the matrix, do the actual math of the rotations, I could say for the two spin system, an X rotation, if it's non-selective, is the rotation by an angle alpha on the I spin, direct product with rotation by an angle alpha on the S spin. And again, I get a 4x4 matrix. If I thought I had a selective pulse that only acted on the I spin, then the second operator would be the identity operator. Nothing happens. Or if I was selective for the I spin, the S spin, this first rotation would just be an E. Nothing happens to the I spin. Alpha here is the rotation angle, not the alpha spin state. This is 90 degrees, for example. And then I have to work out all the matrix math. But I end up with what I already knew. I started with IZ and SZ magnetization, and X pulse rotated to -Y, both components. So the only point of doing all the matrix arithmetic is to convince you that everything is self-consistent. You yourself are not going to ever do that unless you program a computer to do it for you. But our symbols would say the next pulse on IZ rotates to minus IY. X pulse on SZ rotates to minus SY. And the omegas here are just keeping track of relative intensities. If I is hydrogen and S is nitrogen, I expect to have way more magnetization from the hydrogen. Well then, if I evolve around the z-axis with the scalar coupling Hamiltonian and chemical shift Hamiltonian, again, I can build up that matrix. Here it is. So I have rotations of the sums and differences of the spins, and then the J couplings. I have to then have my sandwich, where first I pre-multiply by the operator, then my density matrix, and then post-multiply. And again, I have mathematical multiply this all out for me, and I get something that looks pretty messy. This is now the density operator as a function of time while I'm acquiring the signal. And if I want to know what my spectrum looks like, I have to take the trace with the observation operators. So then, of course, I have to generate the observation operator F plus. That's here. I have to multiply these together. I get something new. And then the trace says sum up the diagonal. I mean, this doesn't look very interpretable, but when I sum the diagonal, I end up with my signal being the I frequency plus J, the I frequency minus J. That's a doublet with the same sign. The S frequency plus J, the S frequency minus J, another doublet. Just what I expect. The splitting in hertz is pi J. And my picture here isn't exactly right because the height of these should be proportional to omega I, and the height over here should be proportional to omega S. So the symbols, the matrices give us what we expect, what we know we're going to see on the spectrometer, and humans just like symbols more than matrices. So we're primarily going to use the symbols, not the matrices. We would only really use the matrices if we were programming a computer, or if we were so confused about what the symbols meant that we needed to figure out what the symbols meant by really going back to the matrices, which is what they really are. If we have a selective pulse, then for example, on the I spins, as I said, the second operator would just be the identity. Nothing is going to happen to the S spins when we do the rotation. We multiply everything out and we get what we expect. We've rotated the I spin Z magnetization to minus IY, and nothing has happened to the SZ magnetization. So then we never detect the SZ magnetization, we only see the I spin. This, of course, would happen automatically. For example, if we were talking about proton and nitrogen. If we apply a pulse on at the proton frequency, 500 megahertz, the nitrogen never feels that pulse. It's just way too far away. So we would expect to only see the proton signal, and that's what we see. And let's see where we are. This might be a good place to stop. Now, maybe we'll stop a little bit early today. This is a good point. You've covered a lot. Take a look. I'll upload this lecture about how the different magnetization components can be labeled and become antiphase with respect to each other. It has an introductory part that kind of makes up the fact that these symbols have to be orthogonal to each other, because that lecture was intended not to show the quantum mechanics. So a little bit in the beginning is redundant, but then there'll be pictures like what I drew on the board justifying that these symbols make sense when we go to the spectrometer. So I'll upload that, and next, by Wednesday, you'll have plenty of time to think up questions, because this is the critical point. To understand how we got here, the rest is practice, 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 and we'll just keep practicing. Any questions online? Okay, good. See you on Wednesday.
Bye.